All right, so let's go ahead and consider a positively charged plate here and a proton or some positive spherical charge. Now we know that the field coming from the plate is going like this because we define an electric field by placing a test charge there and seeing where it goes. And if we were to push this positive charge towards the plate, right, we know that we would have to be doing work to do that. We have a displacement here from here to here. We would have to force it to do that. Wouldn't naturally want to do that. So we would bring it from there to there. So it takes work to do that. It's a force over displacement. And so when we define potential difference, or electric potential difference, it's the work done per unit charge to move a point charge from one point to another. So the work that it took to bring this positive charge from here over to here is, per charge, the potential difference. So what we do is we take how much work that is, however much work that it took, and we divide it by whatever charge that we have. So if we had a larger charge, right, let's say this is, well, this is larger in size, but let's say this had more charge, right, and we pushed it from here to here. Or if we had a small charge and pushed it from here to here, right, we would have a different amount of work. We would, with that large charge, it would be a lot of work over a huge charge. Or if we had a small object, or a smaller one, it would take not so much work and a small amount of charge. They'd all be equal to each other, and that would be a certain amount of voltage from this spot to this spot. So it's a certain amount of voltage irrespective of however much charge that we have. And the work required to move a charge then is, therefore, if we rearrange the equation, voltage times the charge will tell us how much work is necessary. For there to be a potential difference, there has to be an electric field. And so, bringing a charge from one place to the other is, and there's going to be a certain amount of work done there. There's a field there that is going to be in consideration. And so the path taken does not affect the work done. And that's going to be a really important idea here. So for instance, let's say we have a 2 microcoulomb charge and the potential difference or the voltage is 25 volts. Well, we can find out how much work is needed for that to do this. And so we can take the 2 microcoulomb charge, we rearrange the equation, and we multiply the charge times the voltage, and it's going to take 5 times 10 to the negative 5th joules. We convert 2 microcoulombs into coulombs here, and then we multiply it by the voltage. So it's going to take that many joules to move this charge from here to here. Now, let's say we took this charge and we did this, right? We brought it down and then over and so on, right? The only time that we're actually doing practical work is when we're going against the field. So if we're going up here vertically, straight up here, let's say, we're not doing any work. We're not going against any voltage. We're not going against the field. We're going perpendicular to the field, just moving it up, and that doesn't count as work. And so this is analogous to what we did, with work in your junior year, where we only consider work is where the force and the displacement are lined up, and that counts as work. And so this would be the same amount of work. We take it through the same amount of voltage, and the path would not matter. All right, so I'm going to have you try this one. If it takes 1.5 times 10 to the negative 4th joules to move a 2 microcoulomb charge from here to here, what is the potential difference? And so go ahead and pause the clip and do that, and then when you're ready to check, you can hit play to continue. Okay, so voltage is work over work per unit charge. That's voltage. And we divide our joules divided by the coulombs here, so that would be 75 volts would be the movement from the one side to the other. All right, so let's take a look at this situation. We have a field, we have a negative charge, and let's say this is just a single electron, so 1.6 times 10 to the negative 19th coulombs is the charge. And let's say that the potential difference from this spot to this spot is 1 volt. So an electron volt, and this is a key term that we're going to use, a key value that we're going to use, is the work done when a charge equal to 1 electron is taken across a potential difference of 1 volt. And so in other words, taking this charge from here to here. Now, remember how we define an electric field, right? If we place the proton here, it's going to go this way. So naturally, right? So this electron will naturally actually want to go this way. So if we're pushing it, let's say we're pushing it from here to here, it's not naturally going to want to do that. But let's say we did that. We pushed it from here to here over 1 volt. The energy in joules, to be able to do that is corresponding to an electron volt, how much it takes. And so if we consider that, we have voltage equals, work done per unit charge, and we multiply that to those two, it's going to take 1.6 times 10 to the negative 19th joules to be able to do that, which is the same as the charge of an electron because we're multiplying the charge of an electron by 1 volt. And so I put a bunch of stars here because this is really, really critical that you can be able to do this. And electron volts are extremely helpful not only in static electricity, but also especially as we get into quantum and nuclear physics. Using this as a value, because we're dealing with such small values, this can be really helpful. And so this is the most logical place to talk about this, and we're going to need this, really through the rest of the year. But this is how many joules it takes to push that electron from here to here over that 1 volt. All right, so in this one, a proton is accelerated from rest by a potential difference of 5,000 volts, and we want to find the final velocity after it's accelerated. And we want to determine the potential difference required to slow it down to half its speed. So that'll be the second part. So let's go ahead and draw the situation. We have our proton, we've got our electric field, and the potential difference is 5,000. And so the intuition with this, you can think about this, right? It's going to be accelerated, and we can figure out how much it's going to be accelerated because we know how much voltage we have. We also know it's a proton, so we know the charge, right? And so we're going to be able to figure out, and again, it's starting from rest, to be able to figure out, what's happening here. And what we're going to concentrate on is what's going on with energy. So we know the initial velocity is 0, final velocity we don't know. It's 5,000 volts, and we can consider this in terms of again with energy. Voltage is how much work per unit charge, and we've got that right. So we have 8 times 10 to the negative 16 joules, or 5,000 electron volts of energy that this particle is going to receive. So what I want you to do is try to finish this. You're going to need your data booklet to get the mass of the proton and try to figure out what the final velocity will be. And then for part B, well, we'll get to part B in a second. So go ahead and try that first. Go ahead and pause the clip and give this a try. And then when you're ready to check, you can hit play. All right, so that energy is going to turn into kinetic energy. It's starting from rest, and then it's going to turn into kinetic energy. We can figure out what that'll be. We know the mass here. We've got the energy, and it should go 9.79 times 10 to the 5th meters per second. That's how fast it'll be moving. So what we now want to find in part B is, okay, let's say that we shut off the electric field, and it's going at this velocity, and we want to set up a field opposing the motion, going against the motion, to slow it down to half its speed. And we want to figure out how much voltage it'll take to do that. So I'm going to have you try to figure that out as well. So go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. Okay, so half its speed would be 4.89 times 10 to the 5th meters per second. That half its energy, well, it wouldn't be half its energy. It's actually going to be 2 times 10 to the negative 16 joules, with half its speed because velocity is a squared relationship here. And yeah, so we would figure out the potential it takes to do that. And so the loss of energy would be from, we started with 8 times 10 to the negative 16 joules, and then we finish with 2 times 10 to the negative 16 joules. So how much energy will that take? Well, we have the loss of, we subtract those. We have a loss of 6 times 10 to the negative 16 joules. So we're going to need that much energy to slow it down. And so we'll place that in for work. It's going to take 6 times 10 to the negative 16 joules to slow it down to half the speed. And so the final result is it's 2 times 10 to the negative 16 joules. And we get the final value of 3,750 volts to slow it down. Now, to visualize that, what would happen is, right, this is accelerating up and it's getting up to a final velocity. And then to slow it down, we would actually have to reverse, we'd shut this field off and then reverse the field in the other direction. And if we had this much voltage as it passed through, it would slow down to half the speed, and the energy would then be 2 times 10 to the negative 16 joules. Okay, an electron is accelerated from rest in a vacuum through a potential difference of 2.1 kilovolts. And deduce the final speed of the electron that'll be going with, and they give you the answer here, 2.7 times 10 to the 7th meters per second. This is a former standardized question. And so, why don't you go ahead and give this a try, and you can use the data booklet for your information, and then when you're ready to check, you can hit play to continue. Okay, so our field set up, and this is going to be going against the field, and it's accelerated from rest, 2100 volts, and same process here that we did before. We know the charge, we know the voltage, and this is the energy it's going to receive by going through that potential difference, and all of that energy is going to turn into kinetic energy. So it should be going 2.7 times 10 to the 7th meters per second as a result of going through that potential.